In the last video, we looked at how exponential relations look using Desmos. Today, I want to look more at using our exponent rules to create a table of values and then to graph it by hand. So for this first one, we're going to make a table of values, sketch the graph, then describe its characteristics. For characteristics, basically it's all we need to know is whether it's increasing, by what factor it's increasing or decreasing, and what the y-intercept is. So what we're going to do, just like we would with any other equation, I'm going to sub in my x value for x here. So 3 to the x equals 3 to the negative 2 I'm going to put in for x, which equals, we remember from our exponent rules that if we have a negative exponent, we want to make that positive. And to make it positive, we have to do the reciprocal of my base. So the reciprocal is basically just flipping my number 3. And any number is always over 1. Any whole number is technically over 1. So what we get is now 1/3 squared. And if I finish that off, if I evaluate that, I have 1 over 3 squared, which is 9. So when x is negative 2, y is 1 over 9. Now I'll go to the next one of negative 1. So when x is negative 1, I'm going to sub that in for x. Again, I'll do the reciprocal because I have this negative exponent, so I get 1 over 3 to the 1, which I know a whole number to the power of 1 is simply that number. So we just get 1 over 3. The next one, I'm going to get rid of this there too. So 3 to the 0, we learned that anything to the power of 0 simply equals 1. So when x is 1, y will also, or when x is 0, sorry, y will be 1. When I sub x equals 1 in for x, 3 to the power of 1 is 3. And finally, 3 to the power of 2. So I sub 2 in for x, so that's 3 squared, which is 9. Okay, so now we can graph this. I'm just going to graph each of these points. So when x is negative 2, y is 1/9, so it's just going to be above the x-axis. When x is negative 1, y will be 1/3, so just a little bit higher. When x is 0, y will be 1. When x is 1, y is now 3. When x is 2, y is going to be all the way up at 9. So 3, 6, 9. Okay, and then you can just draw a line in there, connecting the dots, showing our exponential relation. So in this next one, we have, rather than 3, we have the reciprocal, so 1/3 to the power of x. We'll do the same thing, follow our exponent rules. Okay, so we have 1 over 3 to the power of x. So negative 2 we will do first. And now we have this negative exponent again. To get rid of the negative exponent, we have to do the reciprocal. So the reciprocal of 1/3 is 3 over 1, or just 3. And that makes my exponent positive now. And that gives me 9. When x is negative 1, same steps, we have this negative exponent, so I'm going to do the reciprocal. So 3 to the power of 1. Okay, Okay, because I flipped it, so my exponent was negative, now it's positive. 3 to the 1 is simply 3. 1/3 to the power of 0 to the exponent 0. We know anything to the exponent 0 is always 1. So when x is 0, again, y is 1. 1/3 to the power to the exponent 1 to the exponent 1, my base just stays the same, so it's just 1/3. And the last one, 1/3 to the power of 2. Now, we talked about this briefly. When I have an exponent outside the brackets like this, it needs to go to each number, my numerator and my denominator. So I get 1 squared, which I know is just 1, over 3 squared. And then when I evaluate that, we get 1 over 3 squared. 1 over 3 squared, which is 9. So 1 over 9. So you'll notice, since this is a reciprocal of 3, my numbers are actually opposite. So in the other one, it was 1/9, 1/3, 1, 3, 9, right? As we can see right here. Now with the fraction 1/3, we get the opposite, 9, 3, 1, 1/3, 1/9. So if we graph that at -2, when x is -2, y will be 9. When x is -1, y is 3. When x is 0, y is 1. When x is 1, y is 1/3. And when x is 2, it's 1/9. Okay, so then they're just going to continue on getting closer and closer to this line, but never actually quite getting to it. Okay, and then you can just draw a line connecting your dots, and we have our exponential function again. So one thing we forgot to do, or I forgot to do, was to describe the characteristics. So for this first one, y equals 3 to the x, we know it's increasing. Okay, so it's growing as x gets larger. And it's growing by a factor of 3. Each time it goes over, each time x moves up 1, my y gets multiplied by a factor of 3. Okay, so 1 times 3 is 3, times 3 is 9. My next one times 3, I would have 27. Also, my y-intercept is 0 and 1. Okay, so that's an important one. When I have 1 over 3 to the x, we are decreasing. My y-intercept, again, is 0, 1. Okay, it crosses my y-axis at 1, and it is growing at a factor of 1/3. So basically each time it's dividing by 3. 9 divided by 3 is 3. Divided by 3 is 1. Divided by 3 is 1/3. Divided by 3 is 1/9. Okay, so there we get our characteristics. Okay, we've seen this one before. We looked at this example yesterday, but using Desmos, so today we are going to actually use our exponent laws. So y equals 2 to the x. We'll do the same things with the last ones. I'm going to sub my x value in for x. So I get 2 to the -2. Remember, we don't like negative exponents, so I'm going to do the reciprocal, which makes my exponent positive. So 1 over 2 squared, and 1 over 2 squared, which is 4. So I got 1/4. So when x is -2, I subbed it in, I end up with y is 1/4. Okay, when x is -1, 2 to the negative 1. Negative exponents, again, we don't like that, so I'm going to do the reciprocal. I get 1/2 to the power of positive 1, which will just stay the same, so it's 1/2. So when x is negative 1, we get y equals 1/2. Then to the power of 0, to the exponent 0, we know anything to the exponent 0 equals 1. And so when x is 0, we have y equals 1. So there, our y-intercept again is 1. Then I do 2 to the power of 1. 2 to the power of 1 equals 2. Then finally 2 squared is 4. Okay. So again, we'll graph that one. When x is negative 2, we get a quarter. When it's negative 1, we have a half. When it's 0, it's 1. When x is 1, y is 2. When x is 2, y is 4. So in this one, since my common factor is 2, or my common ratio is 2, every time it's multiplying by 2. So 1/4 times 2 is a half, times 2 is 1, times 2 is 2, times 2 is 4. If I go another one, times 2 would give me 8. So that tells me at 3, I'd be up to 8. Okay, so you can draw a line, connect those dots, and there we have our function 2 to the x. And 2 to the x, for characteristics, we have it's increasing by a factor of 2, and the y-intercept again is 1. So write those down. Okay, so this one's different than everyone we've looked at so far. We get this number in front of our base. So our general equation we've looked at for an exponential function is a bracket b to the x. Okay, where b is actually my y-intercept. Sorry, no, my common ratio. And a will actually be my y-intercept, which we're going to see now. So if I'll do the same things, only now after I solve this part, I have to multiply each one by 2. So I still have, I got my 2, and then 2 to the negative 2, which we found out in the last one is 1/4. So this is when I sub negative 2 in for x, I get 1/4. 2 times 1/4 gives me a half. If I have 2 quarters, it makes half. Okay, now if I sub negative 1 in, we know 2 to the negative 1 was a half, so I have a half inside my brackets now. And I need to multiply that by 2 because of this a value out front. So 2 times a half gives me 1. So if I have 2 halves, that's 1 whole. So when x is negative 1, y is now 1. When x is 0, sub 0 in for x, so 2 to the 0 is 1. 2 times 1 is 2. Then sub 2 in, so sub 1 in, 2 to the power of 1 is 2. 2 times 2 is 4. And finally, sub 2 in for x. We get 2 to the power of 2 is 4. Multiply 2 times 4, and we get 8. So to graph this one, we'll do our same thing. When x is negative 2, okay, so x is negative 2 right here, y is going to be a half. So it's going to be halfway up 1. When x is negative 1, y is 1. When x is 0, y is 2. When x is 1, y is 4. When x is 2, y is 8. Okay, so we can draw another line along here and then increasing exponentially. So the characteristics of this one are a little different from 2 to the x. The biggest thing is it's increasing at a faster rate. Okay, so at 0, 2 to the x started at 1. 2 times 2 to the x starts at 2. Then this one goes up to 4. The first one only went up to 2. Then to 8. This one only went up to 4. So this one's growing at a quicker rate. Still by the common ratio, of 2. But since we have this number out here, that is our y-intercept actually. So technically, in this one, we would have a 1. Sorry, I'll make that a little smaller. We would have a 1 outside of these brackets. So my a value in this one is technically 1. We just don't need to show it since we assume it's 1. So that tells me the y-intercept is 1. In this one, since we have a 2, that tells me my y-intercept is 2. So the characteristics are it's increasing by a factor of 2, and it has a y-intercept or initial value of 2. So here's just a little summary of that. It has the two graphs side by side for y equals 2 to the x and y equals 2 times 2 to the x. So y equals 2 to the x, we have our y-intercept of 1 compared to this one, which has a y-intercept of 2. It doubles to 2 to 4 to 8. This one, it also is doubling, but it just has a higher initial value, so it's going to be doubling quicker. So it goes to 4 to 8 to 16. So for the equation y equals a times b to the x, greater values of a cause the graph to grow faster. If a is positive, the values of y are positive. If a would happen to be negative, the values of y would be negative. So if I came across an equation that had a negative value for a, so let's say y equals negative 2 times 2 to the x, it would be this same function, only it would be flipped across my x-axis, and it would actually start over here and then grow like that. Okay, just a mirror image of this one underneath the x-axis. So let's look at one word problem. This is question 6 from your textbook. York Region's population, P, okay, so we're representing P for population, is projected to grow until the year 2031 based on the relation P equals 610,000 times 1.029 to the power of n, where n is the number of years after 1996. So years after 1996, that means if 1997 would be 1 year after, so we would be 1. 1998 is 2 years after, so that would be 2. So let's simply calculate the y values for this. I'll do a couple of them, and then I think you'll get the gist of it, and then I'll show you the graph over here. And then we'll look at how to project populations in certain years. So I'm going to get my calculator here. We have P equals 610,000 times 1.029 to the power of n. So this says x, that should say n. My y shouldn't be y, it should be p for population. So when n is 0, I'm going to sub that in. So n is 0, so I have 1.29 to the power of 0, and that equals 1, times 610,000 equals 610,000. So I'll put that in here. We get 610,000 people. So like I said in the last example, this number is actually my initial value. So in 1996, we have a population of 610,000. 1 year after 1996, which would be 97, we're growing at this rate of 1.029. So I'm going to go again, just use my equation. I'll clear this. 1.029 to the power of 1 is 1.029. Multiply that by my initial value of 610,000, and we're now up to 627,000. That's way too high. I punched in one too many zeros. Let me try that again. 1.029 to the power of 1 is just going to be 1.029. Multiply 610,000 equals 600. So now, after 1 year, the population has already grown to 627,690. For the next one, I'm now going to sub 2 in for n. So 1.029 to the power of 2 equals that, times my initial value of 610,000. And we get 645,893. 645,893. So I'll let you finish that off. I'd like you to fill these out before class tomorrow, just to get a little bit of practice with it. Now, what I'm going to show you is how to project the population for these years. Okay, so we need to find out the number of years after 1996. So to find that out, for 2015, what I would do is just go year 2015. 2015 minus 1996 will tell me how many years have gone by. So 2015 minus 1996 tells me that is 9 years after. Okay, so 19 years after, sorry. So to figure it out now, I'm going to use this value of 19 for my n. So I will use my equation, P equals 610,000, 1.029 to the n, where n must be 19. So 1.029 to the power of 19 multiplied by my initial value of 610,000, and we get we're actually at 1,050,079 people. So I will write a therefore statement. So therefore, in the year 2015, it is projected that the population will be 1,050,078. Well, 79 since we'd have to round up. All right. So also before class tomorrow, I would like you to try out this year, 2031. So you'll do the same thing. You'll do 2031 minus 1996. That will tell you how many years after it is. Then you will sub that in for n and just use this equation to find the population. Okay, I hope this helps. I'll see you in class.